There is some confusion about what. Oh, okay, then I will just restart to be complete. Okay, so last time we spoke about light matter interaction, where we split the Hamiltonian into a Hamiltonian for the matter only, light only, and light matter interaction. Then we don't want to treat the light quantum mechanically. So that is the field of quantum electrodynamics. We leave that out. We consider instead the light as a wave. And what we're interested in is how the matter behaves when light is incident on it. Okay? We're not concerned about the light per se or what happens to it when it is reflected off matter. Then we try to represent light in terms of potentials. So normally they are represented as fluctuating fields, but if we want to introduce it into our Hamiltonian, it has to be in terms of potentials. So the most general form involves a combination of the vector potential and the scalar potential. But because of the gauge freedom available to us, we can select some things or simplify it. So the first thing that we do is that we set the scalar potential to 0. This I found out later is called the Weil gauge, if you want to be accurate. And then we also set the divergence of A to 0, which is called the Coulomb gauge. Now sometimes you will see that these two conditions together are also referred to as Coulomb gauge. So this is some sort of ambiguity in naming, but that doesn't matter as long as you remember what is happening. So here both phi is 0 and divergence of A is 0. Then when we solve the Maxwell's equations for these potentials, then we get a unique solution only because we have set these gauges. If you didn't, you would get a family of solutions. And we found that the representation of light in terms of a vector potential is basically this, where you have only one time dependent vector potential. Okay? And it involves the wave vector of light, which is basically in the direction of propagation of light. And you have the electric field polarization vector, epsilon. And you can also and you can show that the wave vector is perpendicular to the electric polarization vector from the fact that the divergence of A is 0. You can also represent the vector potential in terms of the magnetic polarization vector, and that can also be shown, which is this small b, and you can also show that that is perpendicular to both k and epsilon. So the fact that we say that in light the electric field, magnetic field and direction of propagation are all mutually perpendicular, that is taken care of. Okay. Then we also obtained the expressions for the electric and magnetic field, and that you can see is exactly what you normally use in the field representation. Then once we have the potentials in a representation of light, we can simply introduce it into the Hamiltonian. So in one of our very first lectures, we had shown how to get the Hamiltonian for a system of charged particles interacting with a magnetic field. So this is basically the same, except for the fact that here the magnetic field is time dependent, and hence the vector potential is also time dependent. Okay, so that is the only difference. And also we remove the scalar potential term because we have considered the Weil gauge. Okay. So then from here, the next thing that we want to do is we want to derive the electric dipole Hamiltonian. Okay, so that is the approximate Hamiltonian which is used when we are talking about electric dipole transitions. Fine, which is the most But okay, we'll see. Let's see. So let's see. So now we want to do the electric dipole Hamiltonian. So what is that? So what is done is you basically expand this term in the Hamiltonian, knowing that P is equal to minus IH cross del, then I can write H as some H0. If I expand this, so this also we have done before when we were talking about the diamagnetic and paramagnetic interactions. So then we split it up into a perturbation independent part, which is H0, and then we had a okay, I can just write it as P here if you don't mind. It's easier to write it like that. So Pi dot A plus A dot Pi. So this was what we said was the paramagnetic interaction. And then we had a diamagnetic interaction. Right? And we spoke about this before as well, that the paramagnetic interaction is stronger because it is first order in the vector potential, and the diamagnetic is weaker because it is quadratic. So it's second order in the perturbation. Now, when you're talking about this electric dipole Hamiltonian, you basically ignore this. So this is 0. This is ignored in the electric dipole Hamiltonian. So this is considered to be very small because the fields from light are really small. So you don't expect nonlinear effects. However, if you have very intense laser lights or something like this, then you cannot ignore this anymore. But for normal light up to almost up to X-ray, like just before X-rays, you can neglect this A square term. Okay, then you write, then you get your perturbation, the time dependent perturbation that you need to consider is then simply this one term. So that's minus IQi by 2mi PiA plus. Okay, I can put bars on this as well. Anyway, I can put, I didn't put bars on this because these are quantum mechanical operators, but I can. So you can either be very rigorous or you can just consider them to be vectors. So operators, I am not putting hats on. So this is the VT. And this can be also written as now we can simplify this a little bit more. So if we consider del E acting on psi. That is basically divergence of A acting on psi plus A dot divergence or action of grad on psi. Now this is again 0 by Coulomb gauge. So you end up with just A dot grad psi. Okay. So I hope that is clear. And if I want to, then I can simplify Vt as minus some I qi by 2mi, then minus ih cross so I can say this is A dot pi. Okay, fine. Now I don't want to keep carrying the sum over I, which is basically the number of charged particles in the system. So I'll just do it for one particle, and that will also help me avoid confusions with the imaginary number I. So I'll just say the rest of the derivation is for one particle. And then afterwards we'll again put the sum to get the full expression. It's for one particle. So then Vt is equal to...
Excuse me, ma'am.
Yeah?
That 2 will be there in the last P of t equal to?
The 2. No, sorry. No, there will, because there are two terms, right?
2 then.
So there is already A dot del over here. Yeah, the 2 will go away. You're right. So we simplified just this term. So the 2 will go away. That is right. E dot B. Okay. So now let's go back to what we had found A to be. So A was basically this one, right? So I can write A0 epsilon and then e to the power I into k dot r minus omega t. So that is so the vector part is only this electric polarization vector. So I'm doing the dot product of P with that, and the remaining is a scalar part. So k dot r minus omega t plus, I can just say complex conjugate of the whole term. Okay. So then you'll just have e to the power minus I and everything else is the same. Okay. Now here we have another approximation. So this is then comes the long wavelength approximation. Okay. So if lambda is very much larger than the molecular dimension, then compared to the magnitude of r, lambda is infinity. So you can say that lambda is much so lambda, you can say, is infinity compared to r, or the or I should say, what is it called, compared to the, I'm losing the word, so compared to the order of r. So if lambda tends, so k is equal to 2 pi by lambda, right? Therefore, if lambda tends to infinity, k tends to 0, which implies that e to the power I k dot r tends to 1. Fine. Therefore, what we get is, we simply have Vt equal to q by m a0 e dot p e to the power minus I omega t plus complex conjugate. Okay, so that gets simplified. And this is basically what is called the electric dipole approximation. So this fact. Now, why it is called the electric dipole approximation, a little bit of further analysis will show us, but the approximation itself is this one. Okay, so this is basically the electric dipole approximation. Now, if we wanted to go beyond the electric dipole approximation, what would we do? If we then we do not take this lambda tends to infinity, k tends to 0 approximation, but we expand the e to the power I k dot r. We expand it about some center of the molecule R0. So if I say R0 is the maybe center of mass, you can also take center of charge, for example. So you expand it about some suitable point, and then you say that every particle, so you would have a k dot ri when you have multiple particles, and you expand for each term about this r0. So that is e to the power I k dot r0 into e to the power I k ri minus r0. Okay, so I have written ri as r0 plus ri minus r0. So I have a difference quantity here, and then I can expand it to give me r0 1 plus I k dot ri minus r0, and then you'll have the square terms and the quadratic terms, etc. Sorry, the quadratic and cubic, etc. Okay. Now, if you include, let's say, this term, then you would be including electric quadrupole interactions and the magnetic dipole interaction, for example. But I'm not going into this. This is just to tell you that from this point, you can also get more accurate interaction Hamiltonians if you want. But for now, we're sticking to the electric dipole. interaction. Okay. So let's go back to the electric dipole Hamiltonian. There we have Vt is equal to Q by M A0 dot P e to the power minus I omega t and minus epsilon dot P e to the power I omega t. Now I got this minus from the complex conjugation of P, is it? Yes, probably. Okay. Now let's remember something else. So the something else was what was A0. So let's go back and see. So we had defined A0 before. Okay. So A0 is related both to the electric field as well as to the magnetic field. So if we like, we can now represent the interaction Hamiltonian or the Vt perturbation part of the Hamiltonian in terms of the electric field. So A0 from here is equal to E0 by 2 omega. So we can use that. By 2 omega. Oh, so I forgot the A0 over here. Dot P minus epsilon dot P to the power I omega t. Okay. And then again we have, if we like, we can write this with the sine omega t. So this is wait, no, we're missing an I somewhere. I think. Okay, so we had E is equal to this one. So A0 is equal to, where did we introduce that? I should have had an I somewhere. Let's see. So A0. This by 2I. So into 2I. So that is just minus 2. If I define it with an I, then I'm missing an I somewhere. No, but this is right. That this minus this. This by 2i is sine omega, sine of x. So what is wrong? Okay, let's see if I proceed without the I, what happens.
Maybe here you will get I anyway because if you see the summation term in the bracket, e power minus I omega t minus e power I omega t is there. From there you will get I.
Yeah, I'll get I. So this will be 2i into this. Let's see. Let's see. No, I'm just thinking if my relation of a0 with e is also fine. Not very sure. Let's see. So this is this. Now finally I don't want an I actually. So if I convert this now to the sine form, I will end up with an I. So that's what I don't want.
Anyway, no problem. You proceed. You can. Something is wrong. We'll come back.
There is an I missing. Okay, somewhere. So this is here. Anyway, so here let me mark it with red. Something is wrong here. So what I want is basically to have minus q e0 by m omega epsilon dot p sine omega t. So this is what I want. Okay, so there is a
Can you just go where
I
you have defined
present.
V of t once?
Yeah, sure. So where I defined a0 or
V of t.
oh just v
From
of t. So this is no actually if I remember correctly then this I now comes from the definition of E0 that we did before. But it seems that the E0 we did before is actually quite okay. So yeah. So we defined it as this, right? Without an I. But it actually has an I. So this is what I am little bit confused about. So I'll mark this part also. So there should have been an I here, but I'm not sure. So maybe when we do this E derivation, this minus del A del T, then maybe we do not end up with an I, is it? No, we have minus I omega. We will end up with an I. And then we multiply by 2i, divide by 2i. And then 2i squared is minus 2. And the 2i in the denominator goes into the sign. That looks fine to me. Let's see. So this becomes plus I omega. when I take a derivative. So this first term gives me a minus I omega, second term gives me a plus I omega when I take a derivative, when I do del del t. Then I take I omega common. So I end up with a minus on this term and a plus on this term. And then I take the minus. So this becomes plus. Okay, just verify these parts at some point. Maybe when you do it, you will realize where we're going wrong. So there shouldn't be an I at the end of this. Okay. So the perturbation should end up real. So I will also try it out again and see what happens. So let me just continue now. So this is fine. So this is where there is some discrepancy. Okay. Then if you look at this term, E0 sine omega t, then that is basically ET. So I have minus Q by M omega, then ET dot P. Okay. And then if you want to have many particles, then the terms which are dependent on the particle is Q, M, and P. So Vt is basically is heat sum I Qi by Mi dot Pi, and you can have E0 by omega sine omega t. So if I wanted the multiple particles. And this is H equal to H0 plus Vt. In this form, this is basically the electric dipole Hamiltonian. Now, why it is called so is because this term, sum Qi Ri. Okay, we'll come to that. Let's see. So now let's make the transition dipole matrix elements. So far we've just got the Hamiltonian. When light is interacting with matter only via electric dipole interactions, which means just this one term. Why it's called electric dipole, I will explain later. So now we're going to do the transition dipole matrix element. So this basically tells you the transition probability from a ground state to an excited state via this interaction. Okay, so transition matrix dipole elements. So if you have this perturbation, a perturbation of a form which is basically just some constant into sine omega t, then by using time-dependent perturbation theory, you can show that the rate of transitions from L to K, let's say, these are two electronic states. Is given to first order by, this is the rate of transition, electronic transition from a state L to a state K. So this is, okay, I'll write W differently. So W is pi by 2H cross. Then it is the magnitude of a matrix element of the perturbation between these two states square. So that is basically K V0L. Okay, this mod square into the fact that the frequency of the light must match the energy difference of these two states. So you can either have a absorption, or you can have an emission. Okay. So this is what you get from first order perturbation theory, time dependent perturbation theory. So I'm not working it out at the moment. You can look it up, or I can do it later. Otherwise, we'll just be going too far away from what I want to tell you. So you can get the rate of transition to be like this, but you can sort of understand. So it depends a little bit on the strength of the perturbation. So whether it can take it from L to K, and it depends on whether the energy of the light matches the energy gap of the states. Okay, and this is of course, so we know what V0 is. So V0 is basically minus Q E0 by M omega epsilon dot P. So this is what we want. So basically the matrix element that you need is only with this part. So this is a unit vector. So that has no role to play in determining the matrix element. So you can say that this is basically M omega K E dot P L. So this is what you need. And how will you evaluate, and this E dot or epsilon dot you can evaluate after you get the matrix element KPL. So what you need basically is KPL. Okay, and you need to get it for every component of P, and then you take a dot product with this epsilon. Although formally I cannot write epsilon outside, because unless I open it up into components, because the matrix element itself is a number. That is why I cannot write epsilon outside. But in principle, basically you need to find out only KPL. So how do you do that? So you do it by using the commutator of the Hamiltonian with R. So that so then we can express P as matrix elements of some function of R as well, because they are related. Remember, in quantum mechanics, P and X are related. So how to do that? So we use the fact that we know the commutator of R and H0. H0, remember, is the unperturbed Hamiltonian. And this is IH cross P by M. So I can write P as basically M by IH cross RH0 minus H0R, right? I can write it like this. Then my matrix element between K and L is simply M by IH cross R, sorry, K R L, and H0 has acted on L to give me EL. Okay. Minus, now H0 is acting on, so H0 is acting on the left, so EK into K R L. Fine. So this is equal to MIH cross EL minus EK KRL. Okay. And this you can write, if you like, as omega LK and KRL. Fine. So this is what is basically called the dipole matrix element. So this is the electric dipole matrix element. So what is basically implemented in a program when you want to evaluate transition moments is this KRL. So you have some representation for the initial and final wave function, and you take an integral of R. So basically x, y, z separately for these two functions, and you evaluate this, and then you just multiply with these constants. So it simplifies it. It's not, you don't even have to take a derivative. So if you just stopped here with the momentum form, then you would have to take derivatives of your wave function when you evaluate the integral. But because of this relation, you can simplify it to just an integral of x, y, and z over two states. Then what? So we can summarize this now, that VKL is basically so V was here, so minus QE by M omega, QE0 by M omega. Then I have M omega LK by IH cross and KRL. Okay, so M is removed, and I can multiply with I, so minus becomes plus, is it? So into I minus I, plus QE0 omega LK by omega by H cross Oh, sorry, what did I do wrong? So, oh, okay. So the energy difference is H cross omega, right? So I can remove the H. Then you have K. We also had an R. Yeah, so this one dot R. Okay. So that looks fine. This was I. So did I get it right? Yes. Oh, I have an I over here still. So EL minus EK. Oh, that is, sorry, one more mistake. So EL minus EK is minus H cross omega. So L is the ground state, K is the excited state. So this is minus H cross omega. So I have a minus over here, and then I have this, and then again a minus, right? Okay, and then again let's go for many particles. VKL is equal to, so which are the ones which are dependent on the particles? It's this one and this one only. So I have minus IE0 omega LK by omega K epsilon dot semi QI RI. And now you see why it is called the electric dipole approximation, because this is the expression for the dipole moment of the molecule. Okay, so this is minus IE0 omega LK by omega K epsilon dot mu L. Okay, so this is basically it. So that is why this is called, this is the electric dipole moment of the molecule. So this is something that depends only on the molecule. So charge of each particle and the position vector of each particle. So this is, so that's why it is called the electric dipole approximation. Okay, fine. And once you know VKL, this is the part you get from your quantum chemical calculation. Then you can go back to this transition rate expression. And that is the only thing that comes from quantum mechanics. The rest are basically just constants. So you get the transition probability. Okay. So that is about the Hamiltonian. Now we have already used or introduced the two forms of the transition dipole moment, which is the length form, which is this one, and the momentum form, which is this one. I can summarize the relation once more just to be clear. So let's see. Where do we get this? So I use the commutator relation, this, right, of R and H0. It is quite straightforward to show this relation, but I will, for completeness and also in case I forget later, I will derive it over here to show that H0 R is equal to minus IH cross P by M. So I'll just do it for one direction. So let's do HX. So what are H0X? So what is H0? So H0 is equal to basically P squared by 2M plus some potential, which depends on X, Y, and Z, into okay. Then the commutator. So this is just a function. So the commutator of V with X is 0. So the only commutators that are non-zero are the ones coming from P square by 2M. So H0 X commutator is equal to H0 P squared by 2M commutator plus Vx commutator, which is 0. And I can open the P square. So even in P square, the Py and Pz components commute with X. So I can just write this as H0 Px Px square by 2M commutator, which is equal to then H0. Oh, sorry. What did I write? I wrote it wrong, right? I should have written this. I was thinking of this and writing something else. Okay, P squared by 2mx. Px squared by 2mx. So this is basically Px. So let's just put 1 by 2m outside, then Px x commutator minus x Px commutator Px 1 by 2m. So Px x commutator is IH cross this is IH cross, no, minus IH, minus, right, sorry, minus IH cross, and then you have xpx is plus, so this is again minus IH cross px. This is equal to 1 by 2m
two of them, so 2px minus ih. So basically, analogously, you can do h0y and h0z. Therefore, h0r is equal to minus ih cross b by m. So this is the source of the commutator. Okay. And then so this tells you that if you take a matrix element of this commutator, for example, now let's say just the x1 between what did I do? KL or LK? I did KL. Okay. So KXL then this is equal to by M K BX L. Okay, and then we can use the fact that we get EL when H0 acts on L, and we get EK when H0 acts on K. So we get EK minus EL KXL, okay, is equal to minus IH cross by M KBXL. So this tells you that the length form of the dipole operator is equivalent to the or is related to the velocity form. So you can have two alternative forms. Now when you have two alternative forms, then for the exact wave functions, if K and L are exact, if K and L are exact, the two expressions are equivalent. But as soon as you have approximations to K and L, then this relation is lost. And then you have to do some theory specific considerations, like whether they are equivalent or not. Okay, so I can give an example. For example, Hartree-Fock in the complete basis limit, you can show that this relation still holds. That if you compute the dipole, the length form in the length form of the dipole matrix element, then it's equivalent to the momentum form of the dipole matrix element. You can also show this for RPA, or response with real orbitals. So these have had to be proven separately. Okay. In general, if you have an approximate wave function, this is not true. Okay, so we will stop here for now, and next day we'll do it for maybe Hartree-Fock and discuss some issues related to this. Okay, like which form is better, what people say, and what sort of theories show this equivalence, etc. Okay, so I'll stop sharing for now. So do you have any questions from today?